What does it mean to stand on the edge of the observable universe? This question ignites the imagination and invites all who ponder it to journey into the depths of cosmic mystery. To understand this, we must first comprehend the concept of the observable universe itself. The observable universe is defined as the part of the universe we can see. It stretches approximately 93 billion light-years in diameter, containing billions of galaxies, all teeming with stars, planets, and potentially life. But beyond this expansive horizon lies the great unknown, a realm that challenges our understanding of space and time. To grasp how we measure such vast distances, let's consider the speed of light, the universal speed limit at nearly 186,000 miles per second. When we observe distant galaxies, we are witnessing light that has traveled for billions of years, revealing a tapestry of the universe in its infancy. Light from the Andromeda galaxy takes about 2.5 million years to reach us, which means we are essentially looking back in time. Imagine standing on Earth and gazing into the night sky. Each star you see is a gateway to the past. The farther away the star, the further back in time you are peering. But what happens when you reach the edge of this observable universe? When we look at the cosmic microwave background radiation, we see a remnant of the Big Bang, a whisper of the universe's fiery birth, occurring roughly 13.8 billion years ago. This ancient light bathes the cosmos, filling the void and providing a boundary to our observable universe. When astronomers use powerful telescopes to peer into this cosmic haze, they can chart the universe's growth and expansion over billions of years. They find a universe filled with mystery, where each cosmic event reveals the structure of reality itself. As we explore these distant galaxies and uncover their histories, we encounter numerous mind-boggling phenomena. Black holes, for instance, warp the very fabric of space and time, bending light into mesmerizing arcs and challenging our understanding of physics. The Milky Way is home to a supermassive black hole known as Sagittarius A*, which lurks at its center. This behemoth, encompassing millions of solar masses, exerts immense gravitational pull, affecting the motion of nearby stars and gas clouds. Studying such phenomenon helps astronomers calculate distances and understand the structure of the galaxy. But as researchers continue to probe these distant realms, they come face to face with an extraordinary realization: the universe is not static, but dynamically expanding at an accelerating rate. This revelation, stemming from observations by Edwin Hubble in the 1920s, led to a fundamental shift in our understanding of the cosmos. It raised further questions about what lies beyond the observable universe. Is there more universe hidden beyond the cosmic horizon? This thought leads us to contemplate theories of a multiverse, where countless universes coexist, forever out of reach. Some physicists posit that these other universes may have entirely different physical laws, giving rise to completely distinct realities. What might exist in such uncharted territories? The answers may forever elude us. As we ponder these cosmic mysteries, we begin to realize that each nearest galaxy or supernova presents not merely a scientific query, but a tantalizing philosophical dilemma. If the universe continues expanding, how does that affect our understanding of existence? What does it mean for our place in this vast cosmos? The boundaries we see may ultimately be a reflection of our own limitations, echoing the struggle to understand something infinitely larger than ourselves. Thus, as we journey through the cosmic horizon, we find ourselves not just exploring the universe, but investigating the very essence of reality. Little do we know that this exploration is just the beginning of unraveling the mysteries of the edge of the observable universe. What awaits us beyond this horizon is still to be discovered. Stay tuned, for the next chapter will delve deeper into how we measure the infinite distances in the cosmos, unlocking secrets hidden in the darkness of space. How do we come to grips with the vastness of space? To fathom the distances that stretch across the universe, astronomers have developed a series of ingenious methods and tools designed to reach beyond the limitations of our senses. Let's embark on a journey through time and technology to understand how we measure the unmeasurable. The story begins centuries ago, long before advanced instruments filled our observatories. Early astronomers like Hipparchus and Ptolemy looked at the stars and created maps of the heavens without the aid of any technology. Their observations laid the groundwork for modern astronomy, but it was not until the 17th century, with the invention of the telescope, that humanity truly began to peer into the cosmos. Galileo Galilei, the father of observational astronomy, pointed his telescope at the night sky in 1609, unveiling a cosmos teeming with wonders. He discovered the moons of Jupiter, the phases of Venus, and the intricate details of the lunar surface. This marked the dawn of a new era, where empirical observation began to challenge long-held beliefs about the universe. Fast forward to the 20th century, when Edwin Hubble revolutionized our understanding of cosmic distances. By observing the brightness of certain types of stars known as Cepheid variables, Hubble found a way to calculate distances to nearby galaxies. The relationship between their brightness and distance became a cosmic yardstick, revealing that the Milky Way was just one of many galaxies within the vast universe. The invention of the Hubble Space Telescope in 1990 further transformed our ability to measure cosmic distances. Nestled high above the Earth's atmosphere, Hubble captures breathtaking images of galaxies, nebulae, and cosmic events. With its precise instruments, Hubble has determined the rate of expansion of the universe, known as the Hubble constant, which currently stands at about 73 kilometers per second per megaparsec. This means that for every megaparsec you move away from an object, it appears to be getting 73 kilometers further away. This is incredibly significant for our understanding of the universe. It tells us not only that the universe is expanding, but at what rate. But calculating distances is just the tip of the iceberg in our quest to comprehend the cosmos. What about regions of space that are simply too far away for even the most powerful telescopes to reach? How do we confront the seeming impossibility of measuring what lies beyond our observational limits? This is where the concept of redshift comes into play. As galaxies move away from us due to the universe's expansion, their light stretches into longer wavelengths, shifting toward the red end of the spectrum. By analyzing the redshift of light from distant celestial bodies, scientists can infer not only their distance but also their velocity relative to Earth. This method has become a cornerstone of modern astrophysics, allowing us to map the universe on an unprecedented scale. The most distant observable galaxies, such as GNZ11, are so far away that their light has taken over 13 billion years to reach us. This means we are witnessing the universe as it was just 400 million years after the Big Bang. Yet, despite these advances, the question of what lies beyond these distant galaxies remains unsettling. Are we merely scratching the surface of a much grander cosmic reality? As we ponder the nature of the universe itself, we encounter yet another layer of complexity, the existence of dark matter and dark energy. These mysterious components make up about 95% of the universe, yet they remain elusive, refusing to be directly observed. This revelation came about during the late 20th century when astronomers noted that galaxies were rotating at speeds too high for their visible matter. The solution? The presence of dark matter, an unseen force that exerts gravitational influence on galaxies. Simultaneously, the expansion of the universe is driven by dark energy, a force counteracting gravity and pushing galaxies apart. The exact nature of dark energy remains one of the universe's greatest mysteries, prompting scientists to devise grand theories and experiments to unlock its secrets. In our quest to measure the cosmos, we find ourselves faced with the paradox of knowing that we can only see a small fraction of the universe. Yet, in that small fraction, every measurement, every observation, fills the fabric of knowledge that connects humanity to the stars. As we conclude this chapter, We stand on the precipice of understanding cosmic distances, yet the horizon still beckons us, inviting deeper exploration into the heart of existence. In the next chapter, we will uncover the gripping tales of discoveries made by groundbreaking telescopes and how they unveil the secrets of the universe, leaving us in awe of the cosmos. When one thinks of the universe, it's easy to imagine distant, twinkling stars. But to truly understand what lies beyond our world, we owe a great debt to the pioneering telescopes that have shaped our view of the cosmos. Each instrument has brought us closer to the mysteries of existence, revealing breathtaking cosmic phenomena and transforming our understanding. Starting with the humble beginnings of Galileo's telescope, we observe how early telescopes drastically changed our perception. The ability to magnify distant objects opened new avenues for discovery and ignited a passion for astronomy that has continued to this day. But it was not long before this simple device evolved into a marvel of engineering, leading to the construction of larger and more sophisticated telescopes. One pivotal moment in this evolution occurred in 1845 with the introduction of the Great Refractor at the Royal Greenwich Observatory. This telescope, boasting an impressive 48-inch aperture, allowed astronomers to see fainter stars and galaxies than ever before. However, it was the invention of the reflecting telescope, pioneered by Sir Isaac Newton, that truly turned the astronomical world on its head. By using mirrors instead of lenses, reflecting telescopes could gather more light while avoiding chromatic aberration, a common problem faced by lens-based instruments. This innovation opened the door to larger telescopes, allowing humans to peer deeper into the universe's secrets. As technology progressed, so did the construction of larger observatories, leading to the birth of iconic telescopes like the Mount Palomar Observatory's Hale telescope. Completed in 1948, the Hale telescope boasts a staggering 200-inch mirror, and it played a critical role in expanding our cosmic knowledge. It was here that astronomers recorded pivotal discoveries, including the first observational evidence of the expansion of the universe. But it was still just the beginning. In more recent years, the advent of space-based telescopes has revolutionized astronomy once again. The Hubble Space Telescope, launched in 1990, has provided breathtaking images and critical data about distant galaxies, nebulae, and even exoplanets orbiting distant stars. Its ability to operate free from atmospheric distortion has given it a unique advantage, allowing it to discern details that ground-based telescopes could only dream of capturing. Hubble's deep-field images, where it focused on a seemingly empty patch of sky for days, revealed thousands of galaxies in a single frame. These observations not only expanded our understanding of galaxy formation but also illustrated how vast the universe truly is. Hubble's work with Cepheid variables further refined measurements of cosmic distances, solidifying our understanding of the universe's age. As we continue to push the boundaries of observational technology, the James Webb Space Telescope, launched in late 2021, promises to take us even further. As the most powerful space telescope to date, JWST seeks to peer into the earliest epochs of the universe, capturing light from galaxies that formed just a few 100 million years after the Big Bang. This endeavor may shed light on critical questions about galaxy formation, cosmic evolution, and the nature of dark matter and dark energy. The data from JWST will allow astronomers to explore new realms of astrophysics, providing critical insights into the formation of stars and planetary systems. By analyzing the atmospheres of exoplanets, we may even uncover signs of life beyond our own planet, reshaping our understanding of what is possible in the universe. Each telescope brings with it a legacy of discovery, transforming our comprehension of the cosmos. With every observation, we uncover layers of complexity, revealing the universe as not just a collection of stars and planets, but a dynamic tapestry woven with intricate threads of history and science. Yet, as we uncover more, the mystery of what lies beyond our observable limits looms larger, teasing our curiosity. In the next chapter, we will discuss the stunning discoveries made through these telescopic advancements, peering into the depths of space and time, and unveiling the universe's hidden truths in ways we never imagined. As our telescopes have opened the universe to our eyes, they have also unveiled remarkable discoveries that have fundamentally changed our understanding of the cosmos. These revelations challenge our perceptions and inspire wonder, leading us to explore deeper questions about the nature of reality. One of the most astonishing discoveries is that of galaxy collisions. When we look at images from powerful telescopes, we often see galaxies interacting with one another, merging and forming new structures. The Hubble Space Telescope captured breathtaking images of colliding galaxies, reminding us that the cosmos is a dynamic place where change is constant. Such events illustrate the complexity of cosmic evolution, reshaping our understanding of galaxy formation and evolution. In 1998, astronomers made another groundbreaking discovery: the universe is accelerating in its expansion. This finding was supported by observations of distant supernovae, which provided evidence that the universe's rate of expansion is not merely slowing down, as previously thought, but speeding up. This revolutionary insight led to the introduction of dark energy, a mysterious force that seems to counteract gravity and drive galaxies further apart. The implications of this discovery are profound. Dark energy is believed to make up about 68% of the universe, yet we know very little about what it is. This enigma captivates cosmologists, who are racing to unlock the secrets of dark energy and its role in the future of the cosmos. Beyond dark energy, we have also witnessed remarkable phenomena such as the detection of gravitational waves, ripples in spacetime caused by cataclysmic events like black hole mergers. In 2015, the LIGO Observatory made history by directly detecting these waves for the first time, confirming a key prediction of Einstein's general theory of relativity. This marked a significant leap for astrophysics, opening a new window into the universe by allowing us to observe events that were previously undetectable. The convergence of these discoveries leads us further into cosmic mysteries. What happens when we reach the limits of the observable universe? Are there additional forces, galaxies, or phenomena that remain hidden from view? These questions beckon us as we strive to push the boundaries of human understanding, probing into regions of space that remain tantalizingly out of reach. As we strive to imagine past the cosmic horizon, we must also confront philosophical questions about our place in the universe. The discoveries we make have profound implications on our understanding of existence and the infinite possibilities that lie beyond. Each revelation is like a thread unraveling the tapestry of the cosmos, leaving us with more questions than answers. One profound question remains: if the universe is ever expanding, and if we can only see a fraction of it, what does that mean for the nature of reality? The answers may forever elude our grasp. However, each step forward in our exploration brings us closer to understanding the universe, and perhaps our own existence. In the next chapter, we will delve into the role of dark matter and dark energy, illuminating their paradoxical presence in the universe and our quest to understand them. What if the majority of the universe is made up of something we can't even see? Enter dark matter and dark energy, the enigmatic components that constitute approximately 95% of the universe, yet remain largely unobservable and misunderstood. To help us comprehend their role, we must delve into what we know and what remains shrouded in mystery. Dark matter is believed to constitute about 27% of the universe and is thought to exert gravitational influence on visible matter. While it does not emit, absorb, or reflect light, its presence can be inferred through its effects on the motion of galaxies. Astronomers first hinted at the existence of dark matter in the 1930s when Swiss astronomer Fritz Zwicky examined the Coma galaxy cluster. He noted that the visible mass of the cluster could not account for the observed gravitational effects. Something was missing. This led to the hypothesis that unseen matter, which came to be known as dark matter, was present. Further evidence supporting dark matter emerged through meticulous studies of galaxy rotation curves, revealing that galaxies were spinning faster than would be expected if only visible matter were present. Dark matter's gravitational influence explains this anomaly, shaping the structure of our universe. In contrast, dark energy is even more elusive, constituting about 68% of the universe. This mysterious energy is thought to be responsible for the observed acceleration of the universe's expansion. Its existence was proposed to explain the acceleration detected through supernova observations, leading to a radical shift in cosmology. But what truly is dark energy, and why is it driving galaxies apart? Theoretical physicists have put forth various hypotheses, from the cosmological constant introduced by Einstein to more exotic ideas like modifications to gravity. However, the true nature of dark energy continues to be one of the most significant unsolved problems in science. As we explore these mysterious entities, scientists have attempted numerous experiments to detect dark matter particles directly. Projects like the Large Hadron Collider, LHC, and underground laboratories are engaged in the hunt for potential dark matter candidates like WIMPs, weakly interacting massive particles. Despite these efforts, dark matter continues to elude direct observation, keeping it wrapped in a veil of secrecy. What does the existence of dark matter and dark energy mean for our understanding of the universe? They compel us to rethink our fundamental theories of physics and the structure of reality itself. If these components are so vital to the universe's existence, what do they tell us about the nature of matter, energy, and existence? As we close this chapter, we stand at the edge of a grand cosmic mystery, intertwined with our exploration of the observable universe. Dark matter and dark energy act as the unseen architects of the cosmos, guiding the formation and evolution of everything we observe. But with each revelation, we realize how much remains to be uncovered. In the next chapter, we'll dive into the philosophical implications of our discoveries, examining what they mean for humanity's understanding of our very existence. Beyond the stars, beyond the galaxies, lies a remnant from the very beginnings of our universe, whispering secrets of creation itself. This is the cosmic microwave background, or CMB, a faint glow that permeates the cosmos, a snapshot of the universe just 380,000 years after the Big Bang. The CMB is often described as the afterglow of creation, a relic from a time when the universe was hot, dense, and filled with ionized plasma. As this plasma cooled, it allowed electrons and protons to combine and form neutral hydrogen atoms. This process set the stage for photons, light particles, to escape into the cosmos, marking the first moment that light could travel freely in the universe. The detection of the CMB in 1965 by Arno Penzias and Robert Wilson marked a turning point in cosmology. They stumbled upon a persistent noise in their radio telescope, which was later identified as the CMB, giving empirical evidence to the Big Bang theory. This discovery was not just a scientific milestone, it was a profound moment that reshaped our understanding of the universe. The CMB is extremely uniform, with slight fluctuations that hold the keys to understanding the structure of the universe. These variations indicate where matter clumped together shortly after the Big Bang, eventually leading to the formation of galaxies and large-scale structures. But what exactly is the significance of the CMB in our quest to comprehend the cosmos? Analyzing the CMB has provided scientists with crucial data about the universe's age, composition, and overall geometry. It is estimated to be approximately 13.8 billion years old, an age consistent with the time since the Big Bang. Evidence gathered from the CMB has led to the conclusion that our universe is flat, with a critical density that allows it to expand indefinitely. This realization raised critical questions about the ultimate fate of the universe, and whether it will continue to expand forever or eventually collapse back in on itself. From these distant echoes emerges another mystery: dark energy. Dark energy is believed to comprise about 68% of the universe, driving its accelerated expansion and raising profound questions. Will this expansion ever halt? Or will the universe, propelled by dark energy, continue to stretch infinitely? As we peer deeper into the implications of CMB studies, we find ourselves standing at the precipice of cosmic understanding. In the end, the cosmic microwave background is not just a remnant of a fiery birth, it is a cosmic goldmine, a trove of information waiting to be deciphered. With every new observation, we peel away the layers of the universe's ancient past, uncovering the mysteries that lie at the edge of our observable universe. What other secrets are waiting for us to uncover within the cosmic tapestry of time and space? As we move further into this exploration, we must turn our attention to the ambitious efforts being made to explore the farthest reaches of our universe, our next chapter. Imagine peering into the heavens, far beyond the reach of our atmosphere, where the universe unfolds in breathtaking clarity. This is the domain of space telescopes, with the Hubble Space Telescope at the forefront. Launched in 1990, Hubble has given us an unparalleled view of the cosmos, capturing images and data that have fundamentally altered our understanding of the universe. Its ability to observe in ultraviolet, visible, and near-infrared wavelengths allows astronomers to gather crucial information about the formation of stars, galaxies, and the expanding universe. One of Hubble's most significant contributions came in the form of the Hubble Deep Field, an image taken in 1995 that revealed thousands of galaxies in a tiny patch of sky. This groundbreaking achievement showcased the sheer vastness of the universe and provided evidence for the existence of many more galaxies than previously thought. Hubble helped unravel mysteries surrounding galaxy formation, leading to better models of how galaxies evolve over billions of years. But Hubble is just the beginning. As we venture further into the cosmos, we find ourselves on the cusp of a new era of exploration thanks to the James Webb Space Telescope. Set to launch in December 2021, Webb is designed to push the boundaries of our observable universe even further. With its larger mirror and capabilities to observe infrared light, Webb aims to peer back in time to capture the light from the first stars and galaxies, formed only a few 100 million years after the Big Bang. As Webb prepares to extend our gaze into the depths of space, we must consider the implications of these discoveries. What will we learn about the early universe, about the conditions that allowed for the emergence of life, and perhaps even about the existence of extraterrestrial civilizations? The potential for groundbreaking discoveries is vast, as Webb will help answer profound questions about the origins of the universe and our place within it. Moreover, the data harvested from Hubble and Webb will complement current studies of the cosmic microwave background, enriching our understanding of dark energy and the fate of the universe. It is a thrilling time to be an astronomer, as each new image taken by these telescopes sheds light on the enigma that is our universe. As we ponder the advancements offered by these remarkable tools, it is vital to recognize that what lies ahead may reshape our comprehension of the universe itself. Will future discoveries unveil a deeper understanding of the cosmos, or will they present more challenges to our current theories? One thing is certain, the universe has secrets, and we are just beginning to scratch the surface. As we stand on this pale blue, staring into the abyss of the cosmos, one question reverberates through the halls of scientific inquiry: are we alone? The search for extraterrestrial life transcends science fiction. It is a profound quest rooted in the very essence of our existence. With the discovery of thousands of exoplanets in recent years, the potential for finding life beyond Earth has dramatically increased. From the icy moons of Jupiter, such as Europa, believed to harbor a subsurface ocean, to the intriguing conditions present on Mars, the possibilities are tantalizing. Missions like NASA's Perseverance rover are currently exploring the Martian surface for signs of past microbial life. Every bit of data returned from these missions adds to the growing puzzle of what constitutes a habitable environment. Moreover, the search for biosignatures, chemical indicators of life, has expanded to include the study of atmospheres around exoplanets. The James Webb Space Telescope will be pivotal in analyzing these distant worlds, searching for signs of water vapor, oxygen, methane, and other molecules crucial for life as we know it. But the search goes beyond mere habitability. As we probe deeper into the universe, we are left with more questions than answers. What would an intelligent extraterrestrial civilization look like? This leads us to the famous Drake equation, formulated by Dr. Frank Drake in 1961, which estimates the number of active extraterrestrial civilizations in the Milky Way. While many variables in this equation are still unknown, recent advancements in technology and exploration have made the quest for extraterrestrial life more tangible. Whether through radio signals picked up by projects like SETI, or the search for artificial structures around distant stars, every effort to seek out life beyond our planet carries the weight of human curiosity. As we gaze at the stars, we're left to wonder, what if we are not alone? Will we ever make contact with these civilizations, or will we remain solitary observers of an infinite universe? As the next chapter approaches, we must explore the technology that could one day allow us to traverse the vast distances between the stars. As we ponder the vastness of the universe, the idea of interstellar travel becomes not just a dream, but a potential reality. For centuries, humanity has gazed up at the stars, igniting our imagination with visions of distant worlds and new frontiers. But can we truly reach them? Current technology is limited, but advancements in propulsion methods offer glimmers of hope. One of the most promising concepts is the idea of using nuclear propulsion to propel spacecraft at unprecedented speeds. Projects like NASA's Project Orion, envisioned in the 1950s, proposed using nuclear explosions to propel a spacecraft by harnessing the immense energy of atomic reactions. While ambitious, the inherent dangers and political implications made it a challenging pursuit. Today, scientists are exploring alternative methods, such as solar sails and electromagnetic propulsion. Solar sails utilize the pressure of sunlight to propel a spacecraft, theoretically allowing us to reach speeds close to that of light over time. Electromagnetic propulsion, on the other hand, could potentially create thrust using magnetic fields, opening up new avenues for deep space exploration. Another tantalizing concept is the Alcubierre warp drive, a theoretical concept that could enable faster-than-light travel. Proposed by physicist Miguel Alcubierre in 1994, it suggests expanding space behind a spacecraft while contracting space in front of it, effectively allowing for instantaneous travel between 2 points in the universe. However, these concepts exist in the realm of theoretical physics and face immense challenges. The energy required for such feats is staggering, and currently beyond our capabilities. Furthermore, the implications of faster-than-light travel raise profound philosophical questions about causality and the nature of time itself. As we move closer to realizing the potential for interstellar travel, it leads us back to our earlier reflections. If we can travel among the stars, are we truly ready to encounter what lies beyond our own planetary home? The next chapter will explore the human impact of our cosmic journey and the philosophical questions that arise as we venture deeper into the universe. As we stand on the brink of exploring the universe, we confront deep philosophical questions about our existence, purpose, and the nature of reality itself. Every discovery made in our quest to understand the cosmos raises questions about what it means to be human and our place in the grand tapestry of the universe. The philosophy of cosmic exploration engages not only scientists but also thinkers from various backgrounds, as we seek to reconcile our newfound knowledge with age-old questions. At the heart of these questions lies the Fermi paradox. If the universe is teeming with potential for life, why have we not encountered any intelligent civilizations? This paradox challenges our assumptions about life in the universe and forces us to consider the possibilities of advanced civilizations existing but remaining hidden. Moreover, the implications of discovering extraterrestrial life would ignite profound changes in our understanding of ourselves. Would it fundamentally alter religious beliefs? Would humanity unite or fracture in the face of such knowledge? The political, ethical, and social ramifications of encountering other life forms are staggering. As we press forward into the cosmos, we must reflect on what it means to be human in the universe. Are we prepared for the responsibility that comes with our exploration? As we consider the vast number of stars and the potential for life, we must also think about our role as stewards of our own planet. The journey into the unknown carries the risk of unforeseen consequences. Are we equipped to handle the moral dilemmas posed by our exploration? As we look outward, we must ensure we do not neglect the pressing issues facing our home planet. In conclusion, the edge of our observable universe is not just a destination, it is a reflection of who we are and what we seek to understand. As we navigate the cosmos, we carry the weight of our hopes, fears, and aspirations. The next steps we take will define not only our future among the stars but also who we choose to be as a species. Let us cherish the mysteries that lie beyond, for they are intrinsic to our journey as explorers of the universe. Imagine standing at the edge of the observable universe, where the light from distant galaxies barely flickers against the vast expanse of nothingness. Now, consider this: what if our universe is just one of an infinite number of universes? This concept, known as the multiverse theory, suggests that the cosmos as we know it is just a fraction of a much larger existence. The multiverse theory arises from interpretations of quantum mechanics and cosmic inflation, where each quantum event spawns a vast set of alternate realities. In essence, every decision you've ever made could have created a new universe where the other option was taken. In 1981, physicist Alan Guth proposed the theory of cosmic inflation, which explained how the universe expanded rapidly after the Big Bang. As this rapid expansion occurred, different regions of space could stop inflating at different times, potentially leading to isolated patches of space, which we call universes. This leads us to a staggering conclusion: the universe we inhabit may not be unique. If the multiverse theory holds true, then somewhere out there, another Earth exists, where perhaps even another version of you might be living a different life. The implications of the multiverse are profound and challenge our understanding of reality. What does this mean for our understanding of existence itself? If there are infinite universes, each with different laws of physics, it might shed light on why our universe has the properties it does. Some physicists even theorize that our universe is merely one bubble in a cosmic foam of universes, each brimming with diverse possibilities. However, skeptics argue that the multiverse theory, while intriguing, lacks empirical evidence. How can we test or observe something that is inherently unobservable? This hasn't deterred scientists from pursuing knowledge about the multiverse, as they explore the mathematical frameworks that describe its existence. The pursuit of knowledge about our universe and beyond continues to push the boundaries of scientific inquiry. As we delve deeper into this subject, consider the philosophical implications. Are we alone, or is our story part of an infinite tapestry of realities? How does this perspective change our view of ourselves in the grand scheme of existence? The multiverse theory may stir more questions than it answers, but it undeniably expands our horizons, inviting us to think bigger and more abstract than we ever thought possible. In our quest to comprehend the edge of the observable universe, we inch closer to understanding our place within it and perhaps find comfort in the knowledge that we are all part of something potentially much larger than ourselves. As we journey further into the cosmos, we encounter phenomena that stretch the limits of human understanding: black holes and wormholes. These cosmic wonders challenge our grasp of space and time, leaving scientists questioning the very fabric of reality. Black holes, forming from the remnants of massive stars after they exhaust their nuclear fuel, are regions in space where gravity is so intense that nothing, not even light, can escape. They reveal the astonishing laws of physics, showcasing the complexities of our universe. When a star collapses under its own gravity, it creates a singularity, a point of infinite density. Surrounding this singularity is the event horizon, a boundary that marks the point of no return. Once anything crosses this threshold, it spirals into the void, never to be seen again. As bizarre as it sounds, black holes can warp time itself. According to Einstein's theory of relativity, time slows down near immense gravitational fields, meaning that while time might move slowly for an observer near a black hole, it could pass much faster for someone far away. One particularly fascinating aspect of black holes is their potential to serve as portals through space and time, if theories about wormholes hold true. Wormholes are hypothetical tunnels connecting disparate points in space-time, allowing for shortcuts across the universe. Think of it as a cosmic bridge, where if one could traverse through it, one could arrive at a distant galaxy instantaneously. In 1935, physicists Albert Einstein and Nathan Rosen introduced the concept of the Einstein-Rosen bridge, a form of a wormhole. Although these models are mathematically sound, we have yet to discover physical evidence of their existence. The challenge lies in the stability of these structures. They may collapse instantaneously, making them impractical for travel. Recent advancements in theoretical physics, however, offer tantalizing possibilities. Astrophysicists are investigating the nature of black holes and wormholes with new observational tools and technologies. The Event Horizon Telescope, which captured the first image of a black hole in 2019, exemplifies this effort. Future missions may unlock deeper mysteries, such as the behavior of matter and energy in extreme gravitational fields. What secrets lie on the other side of a black hole? Could they indeed serve as gateways to other regions of the universe, or even other universes altogether? These questions inspire not only scientific inquiry but also serve as powerful metaphors for exploration and the human spirit's endless quest for understanding. As we ponder the depths of black holes and the mystery of wormholes, we find ourselves on the edge of discovery, teetering between the known and the unknown. What other cosmic phenomena await our curiosity in the vast expanse of space? The adventure to uncover the secrets of the universe continues, beckoning us to look deeper into the infinite. The quest for extraterrestrial life ignites the imagination and curiosity of scientists and the public alike. Are we alone in the universe, or is life a widespread phenomenon? Astrobiology, a multidisciplinary field that merges biology, chemistry, and planetary science, seeks to answer this profound question. From the icy moons of Jupiter and Saturn to distant exoplanets orbiting other stars, researchers are exploring environments that may harbor life. One exciting avenue of research involves studying extremophiles, organisms that thrive in extreme conditions on Earth, such as acidic lakes and deep-sea vents. These organisms challenge traditional notions of habitability and expand the potential for life to exist in varied environments across the cosmos. For example, the discovery of life in the harsh conditions of hydrothermal vents off the coast of Antarctica illustrates that life can adapt to some of the most unforgiving environments on our planet. If life can thrive in such extreme conditions, could it exist in similar environments on celestial bodies like Europa or Enceladus? Both moons harbor subsurface oceans beneath thick layers of ice, making them prime targets for astrobiological research. The Europa Clipper mission, set to launch in the 2020s, aims to investigate the possibility of life on Europa by analyzing its surface composition and subsurface ocean. Additionally, astronomers are investigating exoplanets, planets outside our solar system, that exist in the habitable zone of their stars, where conditions may be just right for liquid water to exist. The Kepler Space Telescope has identified thousands of such planets, with some located in their star's Goldilocks zone. One notable candidate, Kepler 186f, orbits a star about 500 light-years away and has demonstrated conditions that could potentially support life. Yet, the search for extraterrestrial life doesn't solely rely on distant worlds. Despite our exploration of Mars, we've yet to find definitive evidence of life. However, Missions like the Mars 2020 rover, Perseverance, are designed to search for biosignatures, indicators that life may have existed on the red planet in the past. The implications of discovering extraterrestrial life would be transformative, reshaping our understanding of biology and the universe. How would humanity react to the confirmation that we are not alone? The resulting revelation could lead to a paradigm shift in philosophy, religion, and science. So, as we look to the stars, we raise questions that not only seek answers about life beyond Earth but explore what it means to be human in the grand scheme of the cosmos. Join us in contemplating the possibility of life in the universe and the endless implications it holds for our future. As we peer into the night sky, we often forget that what we see is just a fraction of what exists. The light from distant stars and galaxies travels vast distances, carrying with it stories of origins and evolution. But what lies beyond the observable universe? To grasp this concept, we must first understand the very nature of our universe itself. The observable universe is defined by the light that has reached us since the Big Bang, roughly 13.8 billion years ago. But did you know that the universe extends far beyond that? In fact, estimates suggest the universe could be up to 93 billion light-years across. This immense expanse fuels questions: is there an edge? What does beyond even mean? The farthest we can see is not an absolute limit but merely a boundary defined by our current understanding and technology. As telescopes evolve and our techniques improve, we might find ourselves redefined yet again. Imagine a day when we catch glimpses of events that occurred right after the Big Bang, shedding light on the early universe. But there exists something deeper that challenges our perception. The universe is not static, it is expanding. The fabric of spacetime is stretching, and with it, regions of space are moving away from us faster than the speed of light. This phenomenon fuels the enigma of dark energy, a force that seems to drive this acceleration. What drives this force? Is it a fundamental property of space or something that we have yet to comprehend? As we consider the cosmic horizon, it becomes clear that we're traversing not just in space but through time itself. Our observations from different epochs tell us a story not of a single universe but of multiple timelines coalescing into one narrative. The mysteries of the universe remind us that even as we reach the observable edge, the quest for understanding is far from over. What lies beyond may hold the keys to not just the universe's origins but also its ultimate fate. This quest for knowledge drives humanity, inspiring us to explore and innovate beyond known boundaries. Each question we answer leads to more questions, creating an infinite loop of curiosity and discovery. As we traverse this cosmic journey, we realize that every piece of information we uncover not only enhances our knowledge but also enriches our existence. The universe beckons us, inviting us to explore its mysteries as we stand at the edge of understanding, ever curious, ever reaching. So, what truly lies beyond our observable universe? The answers might just change our understanding of existence itself. Have you ever wondered how we map something as vast and incomprehensible as the universe? Cosmic cartography is a field that intertwines astronomy, mathematics, and technology to create maps of the cosmos. By employing advanced techniques, scientists can chart the positions and movements of celestial bodies across the observable universe and even beyond. But how do we draw a map of something that is constantly changing? To begin, astronomers use a technique called parallax to measure the distance to nearby stars. By observing a star from two different points in Earth's orbit, they can calculate its distance using simple geometry. With distances established, they can move on to more complex celestial structures like star clusters and galaxies, understanding their relationships and distributions in the universe. One of the most significant advancements in cosmic cartography comes from the use of large-scale surveys. Projects like the Sloan Digital Sky Survey have revolutionized our understanding of the universe's structure by providing detailed 3D maps of galaxy positions. Imagine this, a group of scientists working tirelessly for over 15 years, collecting data on more than 1 million galaxies. Each data point represents not just a celestial body, but the history and evolution of the universe itself. But mapping the universe goes beyond charting stars and galaxies. Scientists are also trying to map the elusive dark matter and dark energy that make up most of the universe's mass-energy content. They do this by studying how galaxies are distributed and how they move within clusters. By understanding these patterns, researchers can infer the presence of dark matter, invisible to our current instrumentation, yet exerting a gravitational influence. Furthermore, the expansion of the universe adds another layer to cosmic cartography. As space itself stretches, we must continuously adjust our models, leading to a more refined understanding of cosmic distances and the implications for cosmic fate. Yet, the mapping of the universe is not just about the stars, it's also about the stories they tell. Each star, each galaxy has its own unique saga, shaped by gravitational interactions, explosions, and cosmic events. Taking a closer look at these tales helps us unravel the universe's history and future. As we lay down these cosmic maps, we find ourselves confronting fundamental questions about our existence. How do we fit into this expansive picture? What role do we play in the cosmic dance? Each new discovery, each calculation adds to our understanding, but it also brings more questions, reminding us that the universe is full of wonders yet to be explored. The journey of cosmic cartography is not merely about mapping space, it is a quest for understanding our place in the universe. With every calculation, we inch closer to grasping the infinite, leaving echoes of our curiosity across the cosmic landscape. How will the future of cosmic mapping reshape our understanding? Only time will tell. Imagine being able to listen to the universe, to hear the faint echoes of distant celestial bodies communicating in a cosmic symphony. This isn't science fiction, it's the reality that astronomers and researchers are striving for in the quest to detect cosmic signals. For decades, scientists have been using radio telescopes and other technologies to capture electromagnetic signals from deep space, searching for clues about the universe's nature and potential extraterrestrial life. One of the most famous efforts in this domain is the Search for Extraterrestrial Intelligence, or SETI. This program uses powerful radio telescopes to scan the sky for signals that could indicate intelligent life beyond our planet. In 1977, a researcher named Jerry R. Emmon discovered an unusual signal, a 72-second radio burst that seemed to come from the direction of the constellation Sagittarius. This event, dubbed the WOW signal, remains one of the greatest mysteries in the quest for extraterrestrial life. The WOW signal continues to baffle scientists. Despite numerous attempts, it has never been detected again, leading to speculation about its origins. Was it a natural phenomenon or a genuine extraterrestrial communication? Such questions motivate astronomers to broaden their search parameters, employing advanced algorithms and artificial intelligence to sift through mountains of data. But beyond the search for extraterrestrial life, cosmic signals can tell us more about the universe's structure and evolution. For example, pulsars, rapidly rotating neutron stars emitting beams of radiation, serve as cosmic lighthouses. By studying pulsar signals, scientists can glean insights into the properties of matter under extreme conditions. Moreover, the detection of gravitational waves has opened an entirely new avenue for understanding the cosmos. In 2015, scientists at LIGO announced they had detected gravitational waves for the first time, produced by the merger of two black holes. This discovery confirmed a long-held theory and provided an entirely new way of listening to the universe, revealing information about events that were previously undetectable. Currently, astronomers are deploying increasingly sensitive instruments that can detect signals from the very early universe, providing insights into conditions that prevailed shortly after the Big Bang. The implications of these discoveries are profound, challenging our understanding of the cosmos and our place within it. Yet, as we listen to the cosmic symphony, we become acutely aware of our insignificance in the grand cosmos. The universe is vast, and we are merely tiny observers within its expanse, seeking connection and understanding. Every signal we detect, every mystery we unravel brings us closer to the fundamental truths about existence. As we continue to search for cosmic signals, we ponder not just what we will find, but also how it will change our perception of life itself. What if we discover that we are not alone? What if the universe, in its infinite complexity, holds secrets that reshape our understanding of life and intelligence? The quest for cosmic signals is a journey through the unknown, one that intrigues us all and propels us forward. As we delve deeper into the cosmos, we encounter a vast, interconnected network known as the cosmic web. This structure, composed of galaxies, galaxy clusters, and dark matter, represents the universe's largest scale. Imagine stepping back and viewing our universe from a distance so immense that the individual stars and galaxies blend into an intricate tapestry of cosmic filaments and voids. This profound complexity raises vital questions about the origins and evolution of the universe itself. Discovered in the 1980s and 1990s, the cosmic web has transformed our understanding. It illustrates that galaxies are not distributed randomly, but instead form along strands of dark matter, creating a web-like structure with colossal voids in between. Researchers, like astronomer E.P. Hubble and physicist Albert Einstein, laid the groundwork for understanding these structures through observational and theoretical methods. Their perseverance opened the door to measuring vast distances and the arrangement of matter in the universe. Today, telescopes like the Sloan Digital Sky Survey and simulations using supercomputers enable us to visualize the web more accurately than ever. One captivating study revealed that over 90% of the universe's mass is invisible, composed of dark matter. This elusive substance does not emit light or energy, making it undetectable by traditional means. However, its presence can be inferred through gravitational effects on visible matter, such as the way galaxies move within clusters. The gravitational lensing effect, where massive objects bend light, has also provided insights into dark matter's existence. Consider this: researchers have now mapped the distribution of dark matter across hundreds of millions of light-years. This monumental task involves analyzing the light from distant galaxies to explain how they are affected by the mass of unseen dark matter. But why does this cosmic web matter? Understanding its structure is crucial to grasping how galaxies formed and evolved over billions of years. It offers clues about the universe's fate, including whether it will expand indefinitely or eventually collapse. Imagine being able to predict the universe's future